Oh, was the microphone not working all this time? So could you not hear me in the back before? All right, so more glitches resolved then. All right, so next section in the state of research, Ruodan here speaks about bottom-up and top-down detection. To explain a little bit the concept here, by bottom-up we are referring to going from points to lines to planes to objects to assemblies to the whole thing. Top-down means I have my whole data set and I'm trying now to do some sort of a segmentation to cut down from the whole thing to the assemblies to the objects and so on down to the lower levels of detail. I think this is discussed quite extensively in the literature review, and you can see a lot of information on how you can do these things for both bottom-up and top-down. Generally, my experience has been that for infrastructure assets, top-down is a much more robust approach. However, bottom-up can also assist. And to explain why I'm saying that, if you look at this room, if I was to give you a little patch of that wall, what would you see? Well, it's just a plane with a single color. You wouldn't really be able to tell me just from that information whether that thing is a floor or a ceiling or a wall. The reason we know that this is a wall is actually because of its contextual information, its position in space, relative orientation to other objects. And to capture that contextual information, the best possible way is to approach this problem top-down, because top-down is all about context. The next section she talks about is about model fitting and how we fit something to the point cluster. And so just to explain that concept. So in her work, she has effectively two key steps. The first step is I go from points to labeled point clusters, meaning a group of points with a common label saying, for example, all of these points belong to wall object 1. And then from that step, we have a second process, which is, okay, now I have these points. How do I represent them with a higher level geometry? That's the part we call fitting. And fitting can happen with cuboids or simplistic shapes, or it can happen with more complex geometries, such that we retain, as we call, the high-frequency information behind each component. I think this is what's explained in this section. I think. I haven't read the paper in a while. And you can see some examples here of previous work which we have done a while back on fitting various IFC entities in synthetic bridge data. So I'll quickly move on to her method and her steps. I think this is a good figure that shows the process of how we go from a raw bridge point cloud all the way down to a geometric, as we call it, digital twin of the whole process. You can see here the various steps. She starts with what we call manual cropping. That might sound like an onerous job. It's not. It's actually a very simple thing. All Ruodan does here is she runs a very simple PCA to align generally the axis of the bridge with the main axis of the point cloud. Through that, by defining a simple bounding box, you can cut what is outside of the sphere of influence of the bridge. And then maybe the only extra thing is we add some boxes under the bridge, which is where the flow of traffic goes, because we want to remove the ghosting effect of the cars and the trucks that are passing by just cutting out that empty space that we know is empty anyway. Honestly, you can do that in less than a couple minutes. Once you have the cropped bridge point cloud, you move on to this roughly aligned bridge PCD, as I said before, with the PCA alignments. And then you start with the component detection. Slabs, pier caps, piers, and girders. And we have here a hierarchical process of how we find each and every one. I have to see whether she has a second figure that explains this process. No, it's only the overall figure. But I think the other figures here are actually helpful to understand the sequence. So I want to point your attention to figure 6 here. Figure 6 shows her recursive slicing approach. Very early on, Ruodan realized what I said earlier, that no bridge is straight. Okay, no component on a bridge is straight. We have alignments, for example, that look like the figure you see here. And we're talking skews in all dimensions. This is not just a one skew, which is the one you see here. Nevertheless, we have to have a way to separate exactly what belongs to what. And her approach was effectively a recursive slicing approach. Once she defines her major axis, she starts chopping up various sections, and by having thin slices of the bridge, that helps her at least consider temporarily some parts as well, basically a lot more straight than if you had the entire piece. By having that, she can then apply various rule sets to try to understand, well, if I have a very long, vertically long element, that's probably a support versus a short element. And then through these rules, go step by step into separating various assemblies of components. As we said, this is a top-down approach. And then understanding that these things are connected, look for the connecting elements right in between. You can see the same thing here of how it applies from top-down view as she's trying to slice the slabs. It's fair to say that each one of these mini sections is straight enough to be considered straight so that it can be parsed through that algorithm as her process goes along. I'll quickly jump into her results. You can see here her implementation in the Gygax research platform. You can download that platform, by the way, from GitHub. It's open access, freely available to anyone. And in here you can see the various sections and how the components are then separated from each other. And you can see here for different levels of detail how the various components look like once they have been fitted. I can see that the only, there's some numerical figures here. So you can see the error reported in some of the bridges between what we would expect ideally the components to be versus the actual objects. So we're looking at a 4 centimeter error in one case, 12 centimeter in another. This is in terms of fitting. I think this is because she was looking again at idealized cuboids. If you fit that with a more complicated geometry, then you can capture that space quite more effectively. And going back to her previous figure, I think you can see how the results look like. I would say we've almost solved the problem, but of course there's still room for refinement. Okay, it's an interesting space where a lot more work can take place. The other thing, from a conclusions perspective, I'm jumping to the conclusions now, is that this space can also be much further refined also with exploiting machine learning a lot more than we did in our case. The rules we had to a large extent were quite deterministic, and that's why there's a lot of space there to improve them by trying to use them as a starting point as well as the outcomes of the research to try to learn more. These models and the outcomes are available to anyone. We have 15 bridges, all of them from the original point clouds all the way to the final geometric digital twins. So we welcome any group who wants to extend that work to get back to us and ask for the data. I think it's already published online. We'd be happy to point you to its online location. I think that's all I can say with zero preparation. Thank you.